Welcome to lecture number 25 for ECE 461 control systems. Today we're looking at trying to control a DC motor. Now the motor we're looking at is the same one we looked at last week. It's a little Clifton DC servo motor. What I want to do is control the speed and angle of this motor. So that's where we're heading. From before, I can model the motor as a first-order differential equation. The blue line is the step response I found experimentally. The red line is the step response of this first-order approximation. And you can see it's actually a pretty good approximation. So the transfer function, if I'm trying to control speed, is 39 over s plus 6. If I want to control angle, angle is the integral of speed. So it's 39.28 over s times s plus 6. That extra s converts speed to position. So that's the system I want to control. The hardware setup, which is right here, I've got the motor. It's powered by a power amplifier. That's an Advanced Motion Control's 30A8T. That's basically just a big hog and op amp. It's got 24 volts and ground powering it. With that, I can drive plus minus 24 volts at 20 amps. The motor itself, of course, is connected here. The output of the power amplifier goes to the motor. The optical encoder, this guy right here, outputs 250 pulses per rotation. That goes to a little PIC board. The PIC board just counts pulses and measures pulses per second, computes the speed, has an op amp circuit right here. That op amp circuit then amplifies it and outputs it to the power amplifier, wherever it is, there it is, to the power amplifier that drives the motor. Pictorially, this is what you have. I've got the optical encoder, outputs 250 pulses per rotation. The PIC processor converts that to speed and radians per second, compares to my set point, which is either 0, or actually minus 50 or plus 50. Amplify it with the op amp circuit. This is going to be proportional feedback. I'll also do I and PI a little bit later. Amplified drives the motor. So there's your feedback system. What we're going to look at is proportional I and PI compensation and see if the root locus plots actually predict how it's going to behave. So the first part is going to look at gain compensation. Here K of S is just to gain K. I've got my feedback. This is a type 0 system. What that means is we'll have steady state error for step input, and the closed loop pole starts at minus 6 and goes left. So this root locus is kind of boring, actually. It just starts at minus 6, keeps on going. As I pick a different spot on the root locus, I can calculate the gain that I need. And once I find K, I can implement it. So here's an op amp circuit. That op amp circuit is right here. I'll use a decade resistor box for the second gain. That way I can adjust it. So there's your gain. The error constant Kp is just G times K as S goes to 0. And the steady state error is 1 over Kp plus 1. So as I move along the root locus, the gain gets bigger, the plant gets faster, and the steady state error gets smaller. That's what I predict based upon root locus. So now let's try it. What that looks like experimentally is if I have a gain of 1, say 100K resistor right here, apply step input. Here goes, step point is minus 50. And you kind of see the motor's changing speed. Not that easy to see here. Another way to look at it. And hyperterminal. The PIC is displaying the set point, that's the left column, and the actual speed. As I change the set point going from 50 to minus 50, the motor went from plus 18 radians per second to minus 18. Notice this is a type 0 system. I have steady state error. I want to be going 50 radians per second. I'm only going 18. That's with a gain of 1. And if you look at the step response, this is what it looks like. I'm actually going to 36 because I shifted everything so that it starts from 0. And difference between minus 18 and plus 18 is 36. If I want to put the pole at minus 20, I need to adjust the gain to 356K. So this has a gain of 0.356. I now apply step input. The motor changes direction. Again, not really easy to see in the video. But I go to hyperterminal, I see the steady state error is less. I was going 18, I doubled the gain, so the steady state error is now much smaller. In addition, I get a quicker response. Again, the pole at minus 10 says the settling time should be about 0.4 seconds, and that's kind of what you're getting. Pole at minus 20, I should have a settling time of 0.2 seconds. Again, that's what you're getting. So higher gains give you better tracking, quicker system. If I want to put the pole at minus 30, K is increased to 0.611. So here, this is again a 60. And again, the steady state error is less. And you get a quicker system. So that agrees with root locus plots. That's for proportional feedback. Also note that for a type 0 system, I have steady state error for step input. Can't get around it. To fix that, let's use integral feedback. With integral feedback, I just take that second resistor, replace it with a capacitor, and that adds an integrator, pole at s equals 0. Makes me have no error for step input. The transfer function now becomes 39 over s plus 6, giving me this root locus. This is the pole from the plant. That's the pole of the origin from my compensator. These two come together, split apart. And depending upon how I choose my gain, I can have a very slow system, a faster system with no overshoot, or same speed but 20% overshoot. That's what the root locus predicts. To put you at these different spots, all I need to do is change the gain, which is change C. So doing that, I've now added a capacitor. This is 14 microfarads. If I give it a step input, notice the motor is now slowly changing speed. It's slowing down, stopping, now reversing direction. Apply the other step to go plus 50. It stops and goes the other way. What a type 0 system, or what root locus predicts, is that I'll have no error per step input. This is now a type 1 system. The dominant pole is at 0.5, meaning 8-second settling time. So let's try it. 1001, 1002, 1003, 1004, 1005, 1006, about 8 seconds. You can see that on hyperterminal as well. In hyperterminal, here's my desired speed, 50. Here's the actual speed. Okay, notice there's almost no error. There's a slight error because op amps have slight DC offsets. If I tell it to go minus 50, it takes about 8 seconds to get there. And in theory, it ought to be dead on. Not quite, because there's apparently a little bit of resistance across that capacitor that's discharging it. If I repeat for different gains, again, this is C is 14 microfarads, puts the pole at minus 0.5, very slow system. If I increase C, actually decrease C, make it 4.34 microfarads. So here's 4.34 microfarads. That should put the pole at minus 3. What that does is I still have no error for step input, but now we get a much quicker system. The settling time should be about 4/3 of a second. And that's what we're seeing. Tells you to go minus 50, goes minus 50. Tells you to go plus 50, goes plus 50-ish. That's the pole at minus 3. To the pole at minus 3 plus J6, the root locus predicts that if I do that, I'll start having overshoot. So make C 0.87 microfarads. and C goes to minus 50, there's a little bit of overshoot. Briefly it went too high. That's what you see in the red line. And if you look at it, I'm not sure you can see this or not. There is some overshoot in the speed. So again, root locus is predicting the response. Third type of compensator, a PI compensator. PI predicts that if I add a pole and a 0, I can pick the 0 to cancel the pole at minus 6. That just leaves me pole at 0. As I increase the gain, it just goes left. There will be no overshoot. And I can pick any place I want. If I want to put the pole at minus 10, K is 0.254. Put the pole at minus 20, K is 0.509, and so on. So just by adjusting the gain, I can place the poles wherever I want on the root locus. That's what this predicts. So if I try it, here's the PI compensator. I've added a resistor and a capacitor. One of our RC is 6, that cancels the 0, and R sets the gain. If you look at it on hyperterminal, you can kind of see what's happening. So here's the desired speed, actual speed, change directions, boom. Gets there in about 0.4 seconds. And if you plot the response, that's the blue line. If I adjust the gains, make that 509K, and C is 0.328, that should put the pole at minus 20. And you get the purple line. So again, root locus is doing a very good job at predicting how the system is going to behave. Not only does it predict how it's going to behave, it tells me what gains I need to give a very specific response. And root locus really works. So that was speed control. Let's do position control now. To do position control, I just have to change the software so that instead of feeding back the difference between the desired set point and the speed, I'll feed back the difference between the desired set point and the angle. Make that one little change and suddenly get a position controller. What that does, kind of see on the motor here, I'm telling it to go to 5 radians. That's almost 1 rotation. And not a whole lot happens. Let's increase the gain a little bit. So there it goes to plus 5 radians, then minus 5 radians. So that one little difference, changing the software to go from speed to angle, makes it a position controller. So this would be for opening a valve, closing a valve. Now the transfer function becomes the same as before, but plus an S, because the integral of velocity is position, or angle. So we now have an extra pole. I want to design a compensator for this system. So let's start out with just proportional feedback. If I have proportional feedback, what it predicts is I'll start with the pole at the origin, minus 6. These come together, split apart at minus 3. And depending upon the gain, I can get a slow system, a faster system with no overshoot. Then I start getting overshoot. That's actually minus 3 plus J3, got an error there. Depending upon the gain, I can get whatever response I want. So let's start with the first one. Pole at minus 0.3. K is 0.22. And let's go back to hyperterminal again so you can see what's happening. Here, this is my desired angle, 5 radians. There's the actual angle. Hit the button and go from plus 5 to minus 5. Now this is a type 0 system. There should be no error for step input. Actually there is. The reason for that is static friction. If I hit dither on this, start banging the motor, that kind of breaks the static friction and kind of makes the air smaller. But you're fighting static friction. Motors aren't truly linear. You actually have some nonlinearities in them. That nonlinearity, the static friction, is what's causing the trouble. But that's the response at minus 3. I didn't put a pole on the real axis because if the gain's too small, this is what happens. The motor just doesn't budge. I need a certain voltage just to get it to move. If I try the second gain, to put the pole at -3 plus J3, and here you can see on the hyperterminal what's happening. Get hyperterminal to come back. Give a step input, there's a little bit of overshoot. It comes back, that's the purple line. If I increase the gain even further, I get more overshoot. That's the pole at -3 plus J6, the red line. So that's gain compensation. It's again behaving just like the root locus predicts. I don't predict the steady state error, but that's due to static friction, nonlinearity. The linear model doesn't take into account nonlinearities like that. But otherwise, the root locus is predicting how it's going to behave and what gain puts you at a certain spot. Now let's look at a lead compensator. I've already got a type 0 system, so I don't want to add another pole at s equals 0. If I add a 0 at -6, that cancels the pole, and let's push it out to the left, say 3 times further out. That should triple the speed of the system. Now, as I vary the gain, I can move along the root locus, get the same system I had before, but no overshoot, get a quicker system, or a system with overshoot. So what I'm going to do is build a lead compensator. Here I pick 1 over RC to be 6. That cancels the pole at -6. I'll pick this so that the total resistance, 320K, is about 3.2 times the resistance when this shorts out. That puts the pole 3.2 times further out. And adjust the gain with R. As I change R, I can go from a pole at -3, pole at -9, and a pole at -9 plus J9. Again, what should happen is no error per step input, no overshoot, quicker system with no overshoot, and a quicker system with about 4% overshoot. So if I try that, bring up hyperterminal so you can see what's happening. This is the pole at -3. If I give it a step input, again I've got a little bit of static friction causing error for the step input, but no overshoot like I expect. Put the pole at -9. That should be K or R is 2.3 meg. 2.3 meg. Okay, that's a much quicker system. That's the purple line. Settling time should be 4/9 of a second, about half a second. Increase the gain, so I'm now at -9 plus J9, 4.69 meg. I get the red line. Notice there's a little bit of overshoot. Momentarily went to 6 and came back. And you can see that with the motor. Let's bring that up. Overshoot's easier to see with position control. And the motor's not coming up. Well, if you could see the motor, it would spin, then come back a little bit. So let me turn it sideways so you can kind of see it. Nope, it's not working. So, in summary, root locus really works. It's predicting how the system will behave as the gain changes, and the specific response I want, if I plug in that gain to the actual system, I get the response that root locus predicts. So root locus isn't just for thrills and giggles. It really does work. It applies to things like DC motors, water level and tank, jet aircraft, so on. So that's lecture number 25, control of a DC motor. Saying, yeah, you can control the speed, you can control the position. They're both really about the same. Just change the sensor that you're using. And I go from a angle sensor, position control, or speed sensor, speed control. Lecture number 25.